Hello, today we continue with our A-Level Physics Revision series looking at the subject of electricity. And what is electricity? Well, it's a current flowing in a wire. But what actually does flow in a wire? If this is the wire, we actually have a flow of electrons. It's the electrons in the wire that constitute the current. And they will be attracted to the positive terminal, flowing away from the negative terminal. Now, for historical reasons, we always draw the current as flowing in the opposite direction from plus to minus, but in fact the current is simply a flow of electrons which travels in the opposite direction to what's called the conventional current. That's for historical reasons. Each electron carries a charge of 1.6 times 10 to the minus 19 coulombs. And current is simply the flow of charge. Specifically, current is the amount of charge flowing in a particular amount of time. So current is really measured coulombs divided by time in seconds, but usually we write current as in amps, units of amps, after the physicist Ampere. So since it is the electrons that carry the charge, you can say that the current is proportional to the number of electrons per second. Let's see if we can get that just a little bit more accurate. Here is a length of wire, and electrons are flowing through the wire in that direction. And we're going to say that the average velocity, or what we call the drift velocity of the electrons, is v meters per second. We're going to have the cross-section of the wire with an area A, and so in 1 second the electrons will travel a distance of v meters, because they're travelling at v meters per second. Now let's assume that there are n electrons per cubic metre in the wire, and each of those electrons carries a charge q, which we've already said is 1.6 times 10 to the minus 19 coulombs. Well, how many electrons will pass this section every second? Well, this is the volume that will travel in 1 second. And what is this volume? Well, it's A, the cross-sectional area, times V, which is the distance in meters that is travelled in 1 second, times N, the number of electrons per cubic metre. So that's the number of electrons that will pass this point in 1 second. What is the charge, the total charge that will pass in 1 second? Well, it's the number of electrons times the charge on each electron. So that is the total charge passing per second. And charge per second is the current. So the current is simply AVNQ, cross-sectional area times the drift velocity times the number of electrons per cubic metre times the charge on each electron. Now I want to look at voltage, or potential difference. And voltage is the energy per unit charge. Voltage, which is now capital V, is energy or work done in moving charge. So it is measured in joules per coulomb, but we use the term volt. And you get 1 volt when you do 1 joule of work in moving 1 coulomb. Now we can relate the voltage and the current in a simple circuit in this way. Here we have a battery, here we have a resistance. The battery will have a voltage V, the resistance will have a resistance R, and there will be a current I flowing in the circuit. And Ohm's law tells us that V equals IR. The voltage is the product of the current times the resistance. The voltage is measured in volts, the current is measured in amps, and the resistance is measured in ohms. This means that the current is directly proportional to the voltage, and if you plot the current against the voltage, then you will get a straight line, and that will be a straight line that represents the value of the resistance. For any given metal or conductor, there is a formula which relates the resistance to what is called the resistivity. Resistivity is usually given by the Greek letter rho, and the resistance is equal to resistivity times the length of the material divided by the cross-sectional area of the material. So the greater the cross-sectional area, the lower the resistance. The longer the length, the greater the resistance. Now, in fact, Ohm's law is not something that works all the time because it is heavily temperature dependent. By that I mean that if you plot temperature against resistance, you usually find that resistance increases as the temperature increases. And that means that Ohm's law doesn't apply if the temperature is changing. For example, if you take a filament lamp, then when it is cold, that is when you switch it on, its resistance might be quite low. But then as the light heats up in order to produce the light, the resistance will increase. Well, since you've got the same voltage across the lamp at all times, what that means is that when the resistance is quite low, then the current will be quite high. But when it's heated up, then the resistance is much higher and the current will therefore be much lower. And that's why a filament lamp is most likely to blow when you first switch it on, because when you first switch it on it's cold, and so the resistance is low, the current is high, and that's the highest current it will take. If it's okay when you switch it on, the current will gradually fall as the resistance increases as the bulb gets warmer. But there are materials that have what's called a negative temperature coefficient. So if you now plot the resistance against the temperature, instead of going up, which it did here, you find that as the temperature increases, the resistance decreases, and that's negative temperature coefficient. Sometimes you will find that diodes are introduced into a circuit. Diodes allow the current to travel only in one direction, and that's usually represented by the direction of the arrow in the circuit. So if this is a resistance R and here is a diode, it means the current is only allowed to flow in that direction. But the important thing to remember for physics problems is that in order for the diode to work, you need 0.6 volts across the diode, which means that if, for example, you've got a 9-volt battery, 0.6 volts will be needed in order to get the current to cross the diode, and that means that there will only be 8.4 volts of potential drop across the resistance. We know from classical mechanics that power, P, is equal to energy or work divided by time. In electrical circuits, power is the voltage times the current and is measured in watts. Now, since V equals IR, we can then say that P is either VI or V squared over R or I squared R. When the power company sends you their bill for electricity, they will often quote the amount of energy that you have used by taking this formula here and saying that energy is the power times the time. Power is measured in kilowatts and time is measured usually in seconds. But when the electricity company sends you a bill, it will usually tell you how many kilowatt hours you have had. And a kilowatt hour is just an expression of energy. It's the amount of power in watts that has been generated for every hour. We now come to the subject of internal resistance. Batteries have an internal resistance. Every battery generates electricity, usually by chemical interactions in the battery. And the energy per coulomb produced by the battery is called the electromotive force, or the EMF. So here is a diagram of the battery, which has a sort of associated internal resistance times R. This is all inside the battery. And then external to that, we have an external resistance, which we shall call capital R, and we have a current I flowing through the circuit. And the battery produces the electromotive force, EMF, which we call E, and we can say that E equals IR. But what is R? R is the external resistance and the internal resistance. And so you have that E equals IR plus I little r, and that is, as it were, the lost energy, because that's what's dissipated inside the battery and is often a reason why the battery appears to get warm. We now come to Kirchhoff's rules, and they enable us to work out what's going on in an electrical circuit. There are two rules that we need to be aware of. The first rule essentially says that current can neither be created nor destroyed. So if you have a current travelling through a wire, let's call that I1, and then the current is split into two, I2 and I3, at a junction there, then what you can say is that I2 plus I3 equals I1, because there's nowhere else for any additional bits of current to go, nor is there any other source of current. So the I2 and the I3 must together add up to the I1 that contributes to it. And that is Kirchhoff's first law. Kirchhoff's second law says that no matter what kind of circuit you may have, it may have batteries in it, it may have resistances in it, it may have lots of other things in it, but the simple fact of the matter is that Kirchhoff says start wherever you like, call it point A. As you travel around the circuit, you will either have an increase or a decrease in the potential difference. As you go across the resistances, as you go across the batteries, there will be a change in the voltage, change in potential difference. But if you go right the way round the circuit and come back to where you started, then the total change of all the potential difference is equal zero, because you're essentially back to where you started. So there can't be any change. You've effectively been up the mountains and down the mountains, but you get back to where you started. So the sum of all the potential differences is zero. That's Kirchhoff's second law. And that can help us to solve a problem, for example, where we have a battery, a resistance, another resistance, another resistance. Let's call these R1, R2 and R3. We have a current I1, and then the current splits and becomes I2 and I3. I3 comes all the way round here, rejoins with I2 and becomes I1 again. Now, how can you use Kirchhoff's rules? Well, the first thing you can say is that using the first law, I1 equals I2 plus I3. That is true at this junction, where I1 splits up to become I2 and I3, and it's also true at this junction, where I2 and I3 rejoin to form I1. You can also say that going round any part of that circuit, whichever way you want to go, as long as you start in one place and end up in the same place, then the potential difference is going to be equal to zero. So, for example, suppose we go round this bit of the circuit. Then you would say that the EMF of the battery, This is our first circuit, that's this one. You've got the EMF of the battery minus I2R2, EMF of the battery, minus I2R2, because that's the potential drop across this resistance, minus I1R1, which is the potential drop across this resistance, equals 0, because we've gone from here past the battery, where we've got an increase. Actually, I think I've got the battery the wrong way round, haven't I, for this current? That should be there, and this should be the small end here. So in other words, that's the positive side, this is the negative side. And the current is flowing around like this. You've got as you go past the battery, you get a potential difference hike, and then as you go through this resistance, you get a potential difference drop, another potential difference drop, and you end up where you started. So E, which is the potential of the battery, minus I2R2 minus I1R1, gosh, I'm making lots of mistakes, minus I1R1 equals 0. Let's see if we can do better with the second circuit. This is just going round this part of the circuit, and again Kirchhoff's rule applies. This is the second circuit, and here we've got I3R3, that's the potential drop, and we've got to go right round the circuit. So now we're going against the flow of the current. We've got I2 coming in this direction, we're moving in that direction, so that will be minus I2R2, and that's all there is in that circuit. There is no battery, and that equals 0 because the sum of the potential differences is 0. Sorry, I did it right, but I didn't let you see it. So it's I3R3, the current through here, minus I2R2, because we're going in the opposite direction of I2, equals 0. And we can also do the third circuit, which is to go right the way around the outside. That's the third circuit. So let's make sure you can see it. What happens? Let's start here again. So we get E, then we go all the way around here, and the next thing that happens is we get a potential drop across here. The current is I3, the resistance is R3, so it's minus I3 R3. Then we come along here, and now we've got a current of I1 going through R1, so it's minus I1 R1 equals 0, because we've got back to where we started. And with those three equations and that equation, you can calculate what the currents are and what the resistances are. I now want to calculate what the total effective resistance is when you have resistors in parallel. So let's suppose we have a battery, and we're now going to put three resistances, or resistors, in parallel. So we'll call them R1, R2 and R3. And of course we've got a current I, which comes down here, but of course it's going to split into I1, I2 and I3. So we've got I1 coming down this limb, I2 coming down that limb, and I3 coming down that limb. And Kirchhoff's first law tells us that the total current here is equal to I1 plus I2 plus I3, because the current can be neither created nor destroyed. Now, the total voltage or potential difference, or EMF, from the battery is applied across each of these resistors. The total EMF is dropped across R1, R2 and R3. So we can say that E equals IR. In the first case that will equal I1, R1. But that also equals I2, R2, because it is also dropped across this. And it also equals I3, R3, because the potential drop is also across here. And the question we are asking is, what is the combined effective resistance of all those resistors? In other words, we're imagining that we simply have one effective resistance, and that effective resistance equates to those three in parallel. how can we work out what that effective resistance is? Well, that effective resistance, this is E, we have a total current I, and we have what's called R effective. That's the effective resistance. Well, in that case, we would say that E equals I times R effective. Right, now we can use that formula there. And we can say that I is E divided by R effective. That's I. Equals I1. Well, what is I1? I1 is E divided by R1. Plus I2. What is I2? I2 is E divided by R2. Plus I3. What is I3? I3 is E divided by R3. And now you can cancel out all the E's and say that 1 over R effective equals 1 over R1 plus 1 over R2 plus 1 over R3. And that is the formula for calculating resistors in parallel. The effective resistance is given by the formula that 1 divided by the effective resistance of all those three resistors in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And finally, what happens if those resistances are instead in series? That is to say, R1, R2, R3. R1, R2, R3. Again, we've got a total current I coming along here, and that current is going to go through all of those three resistances, one after the other. It doesn't split. There's nowhere for it to split. But this potential E is going to drop across all of these resistors. The whole total E drops across those, but there will be a partial voltage drop, V1, V2 and V3 across those resistances, such that E equals V1 plus V2 plus V3. The total voltage drop is equal to the potential drops across each of the resistors. Well, what is V1? Well, V equals IR, so V1 is simply IR1. What is V2? It's IR, so it's IR2. What's V3? It's IR, so it's IR3. Now, what we're trying to find is what is the effective resistance of those three in series. Just like we did before, we're saying here is our battery, here's our current I, battery has potential E, and we're going through an effective resistance, R effective. And in those circumstances, E equals I, R effective. So we can say that this E here is equal to I, R effective. And now all you have to do is to cancel out all the I's, and you get that the R effective equals R1 plus R2 plus R3, just by cancelling out the I's in all cases. And that's the formula for resistors in series. The effective resistance of three resistors in series. In other words, if you were to replace all those and think of them as a single resistor, what is the value of that resistor? The answer is it is the sum of the three resistances.